Today we are doing a short video on the definition of a derivative. So, what is a derivative? Well, it all starts back from algebra, from the basic slope form equation y equals mx plus b, where m is the slope, which is y2 minus y1 over x2 minus x1, and where b is the y-intercept. So, putting this into perspective for a quick refresher, if you have a graph, and we'll use the graph, for example, of y equals x, the most basic linear function that we have. So any x value, if we pick this to be x1, this to be x2, and we have this to be y1, this to be y2, we can find the slope of this line by using the m formula and plugging in any two values that we get here. So if we want to know, hey, what's the slope of y equals x, this line here, we can use this function m equals and then pick two y values and pick two x values. So x2 corresponds to y2 and x1 corresponds to y1. And so we'll have y2 minus y1 over x2 minus x1. And so let's give these points some value. So since y equals x everywhere for this graph, we can say let this be 2 and let this be 1. So y2 would be 2 and y1 would be 1. And if we plug this into our formula, m equals y2, which is 2, minus y1, which is 1, divided by x2 minus x1, which is 2 minus 1, and this simplifies to 1 over 1, so the slope is 1. And so that's the slope between 2 points of a linear function. And any linear function, it's always going to be the same slope everywhere on this entire function. So, using this, how would we find the slope of a curved function? So let's say we have the function y equals x squared. And it would look something like this, where any point that we choose for x, let's say we have x1 and x2, we would have points here and here, and then we would have this would be y1, this would be y2. And so how would we find the slope of this function? Well, you'd think you could just do the same thing, right? But the problem is, if we're doing that, it's going to give us the slope of the secant line, which is here, secant line, and this is not the actual slope of anything on the graph of x squared. It's the average slope between x2 and x1. So, that being said, Where did my marker go? Okay, so if we use the same formula from algebra um, to find the slope here, we would get the same thing. So let's put some numbers in to make this more obvious first of all. So if x1 is 1 and x2 is 2, then that would mean y1 would equal right here 1 because 1 squared is 1, and y2, which is here, would be 2 squared, which is 4. So if we follow through with our formula for m and we do y2 minus y1, we have 4 minus 1 divided by 2 minus 1. This simplifies to 3 over 1, which is 3. So between x2 and x1, we have a slope, an average slope of 3. So it's averagely increasing by 3 between these points. But it's not a slope of 3 at either of these 2 points. This represents if we had a straight line between them, which we clearly have a curve here. So if I wanted to find the slope of, let's say, um, a point on this curve, for example, right here, we would need the tangent line at this point to say, hey, the slope at this exact point is some number. And so using the definition of a derivative in calculus, we can do this. And that's what makes calculus so wonderful, is it allows us to work with curves and functions that are not linear and to get really important knowledge about them. So let's move down here and let's start talking about how we might be able to do this. So what we just did is we picked 2 points that were spread from each other some distance, right? And we took the average between them, and that was our slope of 3. But if we want to really know, hey, what's the slope of this point or anything in between, or any point on x squared for the matter, we can use the definition of a derivative. So what is the definition of a derivative? Well, let's go back to our nice graph of x squared, and I am only going to draw half of it. We will call this x. We will call this f of x, which is the same thing as y, function of x, just like we label y as when we say y equals x. It's the same thing as saying function of x equals x. So in this case, function of x equals x squared. So we plug in some number for x, we square it, and we get f of x, which is the same thing as y equals x squared. But we're going to call it f of x for now so we can see how this works. So if I say, hey, I want you to find the point, the slope of the point right here at this value, and we will call this x. And so if we want to do that, we need another point usually to find the slope, right? So hang on, let's actually, oops. Let's make this a little bit bigger. So we'll say we want to find the slope here, x. And we need another point to use our formula, right? M equals y2 minus y1 over x2 minus x1. We need 2 points if we ever want to find a slope. But the problem is if we pick any of these points, it's not going to be the exact slope because it's an average. So if we're going to do this, let's say we pick a point all the way over here. Oh, geez. First time making one of these videos. Let's say we pick a point all the way over here, and we're actually going to call it, we can call it x2 for now, but we're going to change that, you're going to see. So if we have x2 here, okay, we can find this slope between these 2 points, but that's not what we're looking for. So we are going to actually call this, we're going to call the distance between these two functions from here to here h. Okay, so if this is x and this distance to the next point is h, then that would mean that we can call it x plus h. And so now we have 2 points in terms of x that we can use to apply our slope formula. So grab a sweet coffee here. So if you have ever heard of something called a limit, a limit tells us to, it says, hey, as this number approaches 0 or whatever limit you're taking, what value are we getting close to? And so we're going to use limits to make us close this space on x so that there's no distance between the 2 points that we pick. However, we're still going to be able to get a slope out of it, and you're going to see how this works. So we're going to say the limit as h approaches 0 of f of x plus h, which would be the y value here. So we can say this is f of x plus h, and we can say this is f of x, and so we're taking the second y value, which is f of x plus h. We're going to subtract, just like we do here, y2 minus y1. We're going to subtract f of x, and we are going to divide by x squared minus x1, or sorry, x2 minus x1, which in this case we have x plus h for our x2 minus x1, and boom. This right there is the definition of a derivative. So what this limit does for us is it says, hey, as this distance between the points goes to 0, what happens? So essentially we're saying, oh, instead of taking the slope between those, we are now going to move this point as close and close and close and close. And as we get closer and closer, we're going to finally get to that tangent line. And so this is what a derivative is. It's the exact slope at a specific point. And if we start applying this formula, you'll see what happens if we simplify it a little bit. First of all, f of x plus h minus f of x divided by x plus h minus x, we'll simplify it to h. Now, when you're evaluating a limit, the problem is you can't plug in 0 while we have an h on the bottom there, because that would make it undefined and it would not be something we can work with. However, if we simplify this, we can we can usually get an h to cancel out here, and that means we can find the derivative there. So if we're going to use the equation we were using earlier, which is for y equals x squared, or f of x equals x squared, now we can plug these values in for f of x plus h minus f of x over h, and we can find the derivative at a specific point. So we want to find it here. We'll call this x. We'll call this x plus h, and we will plug it into our formula here. So starting off, this is f of x plus h, which is the point that we're going to close in on. So if we have limit as h approaches 0 of f of x plus h, so our function, we plug in x plus h to this and do whatever else the function says to do. In this case, we're squaring it, so plug in x plus h wherever you see an x, and then squared, so this represents that. And then we say, okay, minus f of x. So minus, what is f of x? If we plug in x, we get x squared. And this is all going to be over h. So now we can use some algebra to simplify this limit, because right now we can't plug in 0 yet. And so if we square x plus h, we'll have x plus h minus x squared divided by h. So if you do the FOIL method here, you get x squared plus 2xh plus h squared minus x squared divided by h. Okay. Can we plug in 0 yet? No, we can't, because we still have the denominator. So we're going to look for an algebraic way to pull an h out from the top and cancel that one on the bottom, so we can ultimately plug in 0 for h. And so if you notice here, we have x squared plus 2xh plus h squared minus x squared. So we can get rid of those two terms, the x terms, and now we have 2xh plus h squared all over h. So now we can finally pull an h out from the top, and we'll have 2x plus h divided by h. Boom, perfect. We can cancel out the h's, and now we are left with something that we can work with. So as h approaches 0 of 2x plus h. And now we can finally apply the limit here. And if we do that, we can get rid of the notation as well. So we'll have 2x plus 0, which equals 2x. So this is not only the slope at this point, but it's also the slope of any point in terms of x. So to put that into perspective, what we just found is a formula that can tell us 1, 2, 3, any of the slopes at any of the points on the graph of y equals x squared. So if we want to say, okay, well, what's the slope at 1? And we know the y value there is 1. So what's the slope at this point? Well, plug it into our formula. So our derivative is 2x, so 2 times 1 equals 2. So the slope of this line at this point is 2. What about at 2? Well, plug in our formula, our 2x formula, plug in 2. The slope, is 4. What about at 3? Well, 2 times 3 equals 6. So that means that we're increasing by 6 here, we're increasing by 4 here, and we're increasing by 2 at 1. And so that is how we use limits to actually prove and generate the derivative. But of course, there are tricks so you don't have to go through this process every time using limits and such. And that's where we encounter one of the most famous rules in calculus that you always learn first. Well, you learn after this. You should understand this first. But that gets us to the power rule. So, the power rule. And we're going to use this to show that will get the same 2x formula from the power rule as we did from what's called the definition of a derivative, which is what we just went through. So, what is the power rule? Well, the power rule is written out like this. It's n a sub n, not a sub n, n x to the n minus 1. Um, hang on. I'm very in the realm of power series right now. I'm writing this wrong. So the derivative of x to the n equals n x to the n minus 1 every time. So if you have any derivative in the form of x to the n, or if you even have some coefficient in front of it, we can use the power rule to find its derivative very quickly. You'll often just do this in your head. So, for example, if we want to do the derivative of x squared, which is the same one we did earlier, and derivative notation looks like this. It's called Leibniz notation. This is where we say derivative of y with respect to x, which is basically saying change in y divided by change in x. These are the same thing, and so is something called y prime, where it's called prime notation. This would indicate the first derivative, this would indicate the second, and so forth. After 3, they typically write it as a little parenthesis up there so that it doesn't get crazy with a bunch of apostrophes there. But forget about that for a second. And let's go back to finding the derivative of x squared. So this is like an operator telling us, hey, find the derivative of this function. And so what we're going to do is use our formula. And so in this case, n would be 2. And so our formula tells us, hey, take our n, put it out front, and then subtract 1. So we would say, okay, so 2x to the 2 minus 1 equals 2x to the 1, which equals 2x, because x to the power of 1 is 1, or x. So, bingo, look how much quicker that is. We got our 2x, the same as before. Now, I'm going to give an example of when we have, for example, 3x squared. You do the same thing, but now, so you multiply the exponent to the front. So we're going to have 2 times 3 x to the 2 minus 1 equals, where 2 is our n value, and here's also our n value. And so it's going to be 6x to the 1, which equals 6x. So that would be the derivative of 3x squared. So now if we take another derivative, let's say we're taking the derivative of x, which, lo and behold, do you remember from earlier? Y equals x. That's the equation, linear straight through the origin at a 45. So if I say, okay, well, what's the derivative or the slope at any point of x? We can still use x to the n minus 1 formula, except if you want to make it easier for yourself, you can write n in up there as 1, because x to the power of 1 is still x. So it's going to equal 1 x to the 1 minus 1. What is this? Well, it's going to be 1x to the power of 0. Anything to the power of 0 is 1. So 1 times 1 equals 1. So the derivative of y equals x is 1. And now you don't have to use the old m equals y2 minus y1 over blah 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 x2 minus x1. You just always have a way to get the slope at every point on any graph just by finding its derivative. Okay, so now I want to talk about the second derivative, and it's no different than the first. So it's really easy. If we are taking x squared, once again, we're saying, okay, so find y prime, which is, we're going to apply the power rule, so we're going to get 2x as our answer. Now, okay, I want to know so this is y. So what is y double prime? And the answer is, we're just going to apply the same rule again to the first derivative. So if we do that with 2x, first of all, 2x equals 2x to the 1. So if we take that n up front, we have 1 times 2 times x to the 1 minus, 1 minus 1, which equals 2x to the 0, which ultimately equals 2. So the second derivative is 2. Now, what if we want the third derivative? What is this going to be? Well, once again, you can apply the same formula. However, it's going to be a little weird this time at first. So if we have 2x to the 0, because 2 is the same thing, 2 equals 2x to the 0, because x to the 0 equals 1. So this equals 2 times 1, which equals 2. So this, we're going to write it this way because we want to use the power rule. Once you get used to the power rule, you won't ever have to write it like this. You'll just know that every time you have x to the power of 1, then the x is just going to disappear. But if you have x to the power of 0, which is just a constant, any constant, we're going to see what happens here. So what's going to happen? Well, we're going to take that 0 out front. So 0 times 2 times x to the 0 minus 1, which simplifies down to 0 times 2 times x to the negative 1. Well, guess what? We don't care about any of this anymore because we're multiplying by 0. So ultimately, the third derivative is 0, which means that's as far as we can go. Every derivative after that is still going to be 0 because this can be written as 0x to the negative 1 or whatever you want. It's just always going to be 0 because every time we multiply, take another derivative, it's going to go back to 0, like negative 1 times 0 times x to the negative 2. It's still 0. That would be y to the fourth derivative. So that's how you take some basic derivatives. And if we were to graph some of these derivatives, for example, let's start with x squared again. So we'll draw the curve of x squared, not to scale, of course. We'll redo that. It's not perfect, but basically we have x squared here. So x squared. And then if we want to graph the first derivative, the 2x, that would be something like, let's see. So we would increase by 2 for every value of x, but it would be something like that, just going up, up, and away. So what this tells us is anywhere where this is y prime, anywhere where y prime is positive, that means slope is increasing. So throughout this time on this line, for example, our slope, it looks like that, but over here it's bigger and it continues to grow steeper and steeper as we're going up. However, you can see down here the slope is negative, y prime is negative. So that tells us that, hey, at this point, y is decreasing like this, it's decreasing like this, it's decreasing like this, and so on. So it's negative, but this is where it gets a little bit interesting. The slope of the slope, which is y double prime, or the second derivative, would be the slope of our y prime, which we found to be 2. So that would mean if we go up 1, 2, and draw that equation, y double prime, it's a flat line and it's always positive. Um, so that tells us it's something called concave up. And concavity tells you whether the slope is, I'm sorry, it's not, it's not slope is increasing over here, it's slope is positive. That's what I should have said. Um, Slope is positive when y prime is positive. So it's an increasing slope, or the slope is growing, but as you see over here, the slope is not positive, it's going downward, so it's negative, um, where y prime is negative. But y double prime tells us that, hey, since it's always positive, that means that the slope is increasing throughout the whole function. So as you can see, we start off really steep downward, but then we get slightly less downward, slightly less downward. We hit zero right at this point. The slope is like a flat line, so it's a slope of zero. And interestingly, y prime has a y value of zero at this point. It goes right through it. So that would tell us that the slope at that point is zero. And also, though, then we see that the slope continues to increase by a factor of 2, which is y double prime. Okay, so now we will look at something called the product rule. This will probably be the last thing I talk about in this video. The product rule. What is the product rule? Well, if we want to take derivatives of more complex things that aren't as simple as 3x squared or x to the 7th or something easy like that, we want to find derivatives that include multiple functions. So let's say we have um, hmm, okay, let's start easy. Say we have x squared times um, x squared. Let's just make this really easy first of all. So we know that this is also equal to x to the 4th, and we could just find the derivative of this by doing um, the power rule, so it'd be 4x to the 3, right? So that's our answer we know we're looking for. It's not always ever going to be this easy, though. The whole point of the product rule is to help solve harder derivatives that you can't just use the power rule by itself. And so if we're going to have this, we have two separate functions here. We're going to call this one f. We're going to call this one g. And so the product rule says that the derivative of the product of f of g, so dy dx of fg equals f prime times g plus fg prime. So this is our new formula we have here. And if we use that for this, where we have f equals x squared, g equals x squared, and we plug it into this new formula over here, the product rule, we're going to have f prime, which I would recommend just finding f prime and g prime over here first. So what's the derivative of f? It's going to be 2x. What's the derivative of g? It's going to be 2x. So we know those. Now we have everything we need to plug in, and we're going to start with f prime g. So f prime g, so 2x times x squared plus f g prime, so x squared times 2x. And what is this going to equal? So we're looking for 4x to the 3. Well, if we multiply these, we get 2x to the 3 plus the same thing, 2x to the 3. And this equals 4x to the 3 to the third power. So that's the product rule on a very easy one. And so if we want to do this again, I'll write the formula one more time. dy dx of fg equals f prime g plus fg prime. If we want to find this for, let's say, um, okay, let's do 3x squared minus 5x times 9x cubed plus 5x squared. So you could just FOIL all this out and then take power rules of each individual term. But instead, we're going to do the product rule, and we're going to take the derivative of this, the derivative of this, and plug it into our handy formula, and then we'll multiply everything out. So starting off, we have f equals, we'll label this one f, this one g, so 3x squared minus 5x. We'll say, well, let's just take f prime first. So 6x minus 5. Whenever you have something x to the first power, it just becomes the coefficient. And then we have g equals 9x to the 3 plus 5x squared. G prime equals, multiply 27x squared plus 10x. Okay, we have all of our ingredients and we're ready to bake the product rule here. So plugging in f prime g, we have 6x minus 5 times 9x cubed plus 5x squared. And all of this is going to be added to fg prime, which is 3x squared minus 5x times 27x squared plus 10x. Almost ran out of space there. Okay, so this is the derivative. We're done, but you could simplify it by FOILing everything out. And so you could do that, and you usually will have to do that when you are doing your tests and stuff, but it's all easy FOILing. I'm not going to do it, but this is our derivative. We've done it. So now I think that's enough for